Hi, today I'll be talking about image captioning, and this is a project done by myself, Somaya, and my friend Niranjan Jagannath, and we're from Purdue University. So usually it's misunderstood the difference between image classification and image captioning. So what image classification is, given an image, the neural network or any other machine learning algorithm will just classify it into a class or find the object in it. But whereas image captioning is much more complex, where given an image, it has to generate a caption for it describing the objects and the complex relationships that are between the objects in the image. So let's look at how we did this experiment, and we used this data set, which is the common objects in context data set by Microsoft. It has 82,000 images and the corresponding captions which describe each of the image, and we have validation of 40,000 images. And let's look at a video of our results so we know how complex the task is. So this is Niranjan taking a video of objects in our kitchen, and it essentially gives a description or a caption for each of the things that it's seeing. It's able to recognize the sink in the kitchen, and it already did recognize the microwave, and it does really well since it's already a complex task, and network does really well in identifying these objects. And we can also see that it gets the refrigerator as well, and that's me standing there. And it also sees in the frame that there's a laptop, and it finds that there's a laptop and there's a table around. So the network does fairly well, and we'll go about the architecture that we use to solve this task. So the architecture that we use is, we have a deep CNN which essentially has the embedding for the image, and we use a CNN because it gives a rich embedding for the image. Basically it has many components of the image that's embedded in by using the CNN, and this is fed into a recurrent neural network which essentially generates the caption or the words and then combines it to form a meaningful sentence in a task of natural language processing. And then let's go about the CNN architecture. We used ResNet 152, and we removed the penultimate layer, and then we made sure the dimensions fit to the dimensions of the input of the RNN, so that is 256. And this is how we got the embedding of the CNN. And this image embedding is then fed into a recurrent neural network that my friend Niranjan will talk about, and that will generate the captions. He'll also go about some of the images that we use to generate the results.
So here we have the complete architecture of our model. So the image is first input into the CNN, which gets a rich embedding of the image and gives it as input to the first time step of the LSTM. And here we have the unrolled architecture of the recurrent neural network, where each time step produces one word of the caption at a time, and this gives us the flexibility of unbounded length captions. So at each time step, we are trying to maximize the log likelihood of that particular word as compared to the target caption, and the objective of the network as a whole is to maximize the sum of log likelihoods of each words. So here we have S as the caption and I as the image, and we are trying to maximize the sum of log likelihoods of each word at a time step, conditioned on the image input and all the other words captioned before it. So here it essentially gives us the loss function of cross entropy loss, which we use to backpropagate through the network. So coming to training and evaluation, the CNN part is pre-trained on the ImageNet dataset, and all other weights, that is the word embeddings and the LSTM weights, are initialized randomly. We were able to train it for 12 hours on a mid-range GPU, which gave us okay results on our evaluation data. But as we wanted to try something better, we decided to modify the architecture a little to be able to use the pre-trained weights of Show and Tell, which is a paper by Google. Coming to the evaluation part, accuracy and F-score are not good metrics when it comes to natural language processing, as they tend to compare each words of the caption word by word, which is not a good indicator of whether our model has learned to produce natural language. There is also something called Blue score, which matches n-grams without order of both the target and the generated caption, but it has also received backlash over the years. So hence we decided to use our own images as the evaluation metric. So here we have some fun results of the things which our model got right. Here we have a clock tower which is correctly captioned, and here we have our professor holding a remote control, which the model sees it as a cell phone, which is the most probable outcome, I guess. And here we have some OK results. So when it comes to objects which are out of the ordinary, like a mailbox with snow on top of it or a war memorial, the model tries to predict it as something which it has already seen. So here it does not recognize it as mailbox, but it gets the colors right, and here it seems to think it's a clock tower because this closely resembles a clock tower. And when it comes to the realm of unique objects like this fountain in our campus, it's not able to generalize well, and it seems to think it's a fire hydrant. So this is a classic case of data mismatch problem where the training data is not a good predicator of the test data. So if we were able to train our network on these particular images, it would perform better. So that's it for the presentation. If you have any questions, feel free to contact us on any of the mentioned email addresses, and thank you for watching.